All right, hi class, it's Mr. Mellinger. So we're going to move on and talk today about covalent bonds. The last 2 days we've been talking about ionic bonds. Those are the bonds between metals and nonmetals, where the metal will pass an electron, one or more electrons, over to the nonmetal, and they form a positive and negative charge and they attract each other. Now we're going to talk about bonds where the electrons are shared more equally. Those are called covalent bonds. So covalent bonds occur when two or more atoms share electrons. Covalent bonds are bonds that are found in you and other living things. In fact, in other words, virtually all of the bonds in your body are covalent bonds. Covalent bonds occur primarily between nonmetals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, chlorine, and others. And finally, covalent bonds produce combinations of atoms called molecules. They form structures called molecules. So remember, the key word with covalent bonds is that they share electrons. So just as with ionic bonds, covalent bonds use the octet rule. So the octet rule says that atoms are happy when they can fill their valence orbital. Octet means 8, and it's called octet because elements in the second and third periods, that is rows, and even all the elements down below the second row, need 8 electrons to fill their valence outer orbital. So if you look at the oxygen atom, oxygen has 6 electrons in its valence orbital. To be happy, oxygen would like to fill the 2 empty spaces, but how? Well, we've seen how if it's near a metal, it can grab those electrons away from a metal and form an ionic bond. It can get the electrons that way. But what if it's near another nonmetal, one that also has a high electronegativity and really likes to pull on electrons? What happens? So again, the octet rule says that atoms are happy when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period and below need 8 electrons to fill their valence outer orbital. So hydrogen's valence orbital can only hold 2 electrons. So hydrogen needs 1 electron to be happy and fill its valence orbital. But how does it do it? Where does it get that electron from? Note, by the way, that even though hydrogen can only hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So if 2 hydrogens come near an oxygen, each hydrogen shares its electron with the oxygen, and this gives the oxygen a total of 8 valence electrons. So the oxygen is happy. The oxygen shares an electron to fill the valence orbital of each hydrogen, so the hydrogen atoms are happy. So if you look at this configuration, you'll notice that each hydrogen has 2 electrons. That fills its valence orbital. And the oxygen has 8 electrons in its outer orbital, and that fills its valence orbital. You'll notice that those electrons that are shown in pink there, that they're double counted. They're counted as 2 electrons for the hydrogen, and they're counted as 2 electrons for the oxygen in each case. And that's why it's called covalent. It means co means together, and valence means valence orbital. So together, valence orbital, it's covalent. So because hydrogen fills the valence orbital of oxygen and oxygen fills the valence orbital of 2 hydrogens, this combination creates H2O or water. Oxygen is the most common element on Earth. Hydrogen is the most common element in the universe. So the 2 of them together form the most common substance on Earth, which is water. So bonds are created by atoms sharing electrons according to the octet rule. These are called covalent bonds. Covalent bonds share electrons. So what are diatomic molecules? Well, there's 7 diatomic. They really should be called, they're called diatomic molecules of the same element. Diatomic means 2 atoms. There can be diatomic molecules that are of 2 different elements, but in this case we're talking about the 7 that are of the same element. And Diatomic molecules are the most common bonds in nature. There are 7 diatomic molecules. 4 of them are halogens with 7 valence electrons, and they are the ones you can see below: fluorine, chlorine, bromine, iodine, hydrogen, oxygen, and nitrogen. So the oxygen we breathe into our lungs, which is in the air, is an O2 molecule. It's not an oxygen atom. Hydrogen never exists as just hydrogen atoms floating around in space. They always pair up to form hydrogen molecules. They're just simply, that's because these molecules are more stable when they're joined up with another of their own type than they are when they're by themselves. All right, so how does H2O covalent bond work? Well, you saw it earlier. So all atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with hydrogen if hydrogen shares its electron with oxygen. Oxygen repeats this process with another hydrogen. Both hydrogens and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the Octet rule. And covalent bonds form independent structures called molecules. This, by the way, this configuration, this diagram is called a Lewisdot structure, and you're going to learn about that in just a few slides. And there you can see those are the shared electrons. So this is just a different way of drawing the water molecule. Okay, a diatomic molecule is a bond between 2 atoms of the same element. Diatomic molecules are found the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens and 7 with 7 valence electrons. So you can see those 2 empty spaces. And so they can come together, and each of those 2 fluorines, so you see why fluorine would want to come together now, because they can fulfill each other's empty space and fulfill the Octet rule. So compare the kind of structure that covalent ionic bonds form. So covalent bonds form molecules. So this H2O water molecule, for example, is a separate structure from all other water molecules. In other words, when you boil water, the H2O molecules break apart, and they separate from other H2O molecules, and they can float off in different directions. So you can think of molecules like cars. They're separate structures, and they can move off in different directions from each other. Ionic bonds form crystal lattice structures. Think of a lattice structure like bricks in a wall. No one sodium belongs to any one chlorine, or no one chlorine belongs to any one sodium. So if you look at one of those chlorines in either of those diagrams below, there's 4 sodiums around it. Which one does that chlorine belong to? Well, it doesn't belong to any one sodium. It belongs to all 4 of them. So you can think of those chlorines like bricks in a wall, or the other analogy I use is apartments in an apartment building. You can tell one apartment from another apartment in an apartment building, but you can't tear it out. It can't go in its own direction. It can't go off on its own. It's stuck in the apartment building, or bricks stuck in a brick wall. They can't just move by themselves. Whereas molecules, covalently bonded molecules, are separate structures that can move off and move around by themselves. So what is a polar molecule? A polar molecule is a covalently bonded molecule. I should make that point. It's covalently bonded molecule that has a positive side and a negative side. So look at the following water molecule. This is because the oxygen is more electronegative. So the oxygen is going to be that bigger atom down there in the lower left, and it's more electronegative than hydrogen, so it pulls the electrons towards it. So if you look at this diagram, I've drawn it, I've made these separate sections, and you can see that, notice the side of the molecule in pink has 2 protons and no electrons. So if you just looked at what's inside that pink rectangle, you only have 2 positive charges. That means that area is positively charged. That side of the water molecule is positively charged because it has those 2 protons. Those come from the hydrogen atoms. Those are the nucleus of the hydrogen atoms. They are off to that side, and so that side has a positive charge. Okay, now look at the other side of the molecule. The side of the molecule in light blue has 10 electrons. You can count them there. There's 10 total electrons and only 8 protons. Those are the 8 protons in the oxygen nucleus. So it has a more negative charge. So even though a water molecule is electrically neutral, has the same total number of protons and electrons, if you count them all, it does have a side that's more positive and it has another side that's more negative. The side with the hydrogen on it tends to be a more positive side of the water molecule, and the oxygen side, that lower left-hand side, tends to be more negatively charged. So although H2O, water, is electrically neutral, 10 protons and 10 electrons, again, you can count the entire molecule, there's 10 and 10, it has a more positive side and a more negative side. So water is a polar molecule. Carbon dioxide, CO2, has a balanced charge. The two oxygen atoms, which of course have the same electronegativity as each other, pull on the electrons equally, so the charge is equally distributed. So remember that water was kind of a crooked molecule, it was kind of a bent molecule, whereas carbon dioxide, you can see, is straight. And so those oxygens are pulling equally from both ends on the electrons, so the electron charge tends to be balanced in between over the entire molecule. And so carbon dioxide is a nonpolar molecule. It does not have a positive end and a negative end. Okay, Lewisdot structures. You saw one of those earlier, and they're really easy to draw. So Lewisdot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So you remember when we diagrammed atoms, a beryllium atom would have looked like this. Now you're going to see why I had you draw the electrons the way I did, in this case with one on the bottom and one over on the left-hand side, because it has to do with drawing the Lewisdot structure. So the first thing you do is write the atomic symbol. For beryllium, it's Be. The second thing you do is you draw only the valence electrons around the symbol. We don't care about those two core electrons in the first orbital there. We're only interested in the outer orbitals, or the outer electrons, because they're the ones that do chemical bonds with other atoms. So we're going to go ahead and place this one here, and that's it. That's the Lewisdot structure for beryllium. You may say, so what? I mean, what's the point? You're going to find out in this class that we can do some pretty sophisticated analysis of molecules, even complicated molecules, using Lewisdot structures. So even though they look simple, they're used for doing some pretty sophisticated chemistry analysis. So Lewisdot structures show only valence electrons, since only these electrons are involved in chemical bonds. Let's do a couple more. All right, so here's oxygen. That's the way you would have diagrammed it, the way we did earlier in the course. So write the atomic symbol. There's an O. And now draw only the valence electrons around the symbol. So there we go. And that's the Lewisdot structure for an oxygen. You notice it has those two unpaired electrons. That's the key. Those are the ones that the hydrogens bonded with to form water. Let's do one more with phosphorus. Okay, see if you can do this one before I do it. And there it is. There's a Lewisdot structure for phosphorus. All right, so this is basically a summary of how covalent bonds work. You should know this. Covalent bonds happen between two nonmetals. One, nonmetals have high ionization energy and high electronegativity. They're both strong guys. In other words, they like to pull in electrons from another atom. That's high electronegativity, and it takes a lot of energy to take their own electrons away from them, to steal their own electrons away from them, and so that's high ionization energy. So they don't give up their own electrons, and they do like to take in electrons from other atoms. So they're strong guys. Two, both nonmetals pull hard on the electrons of the other atom, but both do not give up their electrons easily. 3. Since neither atom can win that tug of war for the electrons, they decide to share their electrons in a way that they both fulfill the octet rule by having a full valence orbital. Number 4, sometimes this will lead to double and triple bonds. We're going to learn about that in just a minute. And 5, if one of the atoms has higher electronegativity, it will pull all of the electrons closer to it, creating a polar covalent bond. So if two different atoms are together with different electronegativities, even though they're both nonmetals or both strong guys, if one of them's a little bit stronger, it won't totally take the electrons away from the weaker one, the one that's not as strong, but it will tend to pull the electrons toward it. So that side, the one with the higher electronegativity, will be more negative. That'll be a negative side of the polar molecule, and the other one, the one with the less electronegative atom, will be more positive because the electrons are being pulled away from it slightly. All right, we're going to spend one slide on metallic bonds. What are metallic bonds? Copper, abbreviation Cu, easily passes electrons from one copper atom to another. In a metallic bonds, electrons are attracted to the protons in the nucleus, but electrons are not held closely to their own atom or to any particular atom. So they like to jump around from one atom to the next when they're pushed. And even when they're not pushed, they just like to jump around because while they're attracted to the nucleus, they're not attracted to any one nucleus in particular. So it kind of looks something like this. So this is called the electron sea model because the electrons move around like fish in the sea. So they don't just jump from one atom to the other and then stay there, and they don't share electrons. The electrons are really just moving around freely. I mean, they can move up and down the length of a copper wire, for example, and that's what the electron sea model is. Okay, so here's some characteristics of ionic and covalent bonds. So a unit of each. A unit of an ionic compound is called a formula unit or a unit cell, and they form crystal lattice structures. Those are those bricks in a wall or those apartments in the apartment building. Whereas covalent bonds form molecules. Those are separate, independent structures that can separate from each other. When you boil water, two water molecules can float off in different directions. Bond formation. So ionic compounds pass electrons and forming cations and anions from one atom to the next. And covalent bonds share electrons. Elements involved. Ionic are metals and nonmetals. A metal to a nonmetal. And covalent are two nonmetals. Physical state. Ionic bonds are always solid. When you put them in water or liquid, either water or acid, they'll break apart. Whereas covalent bonds can either be solids, liquids, or gases. Melting point. Ionic bonds have higher melting points. The number you see there, 300, is not that important. Ionic bonds generally have higher melting points, covalent bonds lower. One of the projects we were going to do in class is to put both salt and sugar, which look identical to each other to the eye, over a flame, and you'll see that the sugar melts and turns black, whereas the salt doesn't melt. The salt, which is an ionic bond, an ionic compound, has a higher melting point. Sugar is a covalently bonded compound. Solubility in water, meaning do they dissolve in water? Generally, ionic compounds do. We're going to talk about solubility rules later on. Covalent bonds generally don't. And conductivity. Ionic bonds conduct electricity well. You can run electricity through salt water, but you can't run electricity through sugar water, or very little conductivity. So it's very poor. So covalent bonds have poor conductivity. Ionic bonds have good conductivity of electricity. All right, so how do two oxygen atoms have 8 electrons each, form an octet, when they form a diatomic molecule? Because you see, each oxygen has 6 electrons in its outer orbital. So how do you get that? How do you do the arithmetic on that, or rearrange those to get them to form 2 octets? Because 6 plus 6 is 12, and 2 octets would be 16. So how do you get 12 electrons to form 2 octets, which should be 16 electrons? Well, let's see. Each oxygen shares both of its unpaired electrons to form what's called a double bond. So that's a double bond in that yellow area there. notice that each oxygen has 8 electrons in its valence orbital. So again, if you count the 4 electrons in that yellow area, then the oxygen on the left counts those 4 plus the 4 others that are outside of that in the second orbital. That would be a total of 8. And the oxygen atom on the right has those 4 electrons in the yellow shaded area plus the 4 more that are in the second orbital to the right, and so that's a total of 8. So they both think they have 8 electrons, and that's how an ionic bond works there. So that's called a double bond. Excuse me, that's how a covalent bond works when you have in the case of oxygen, and that's a double bond. And here's the Lewisdot structure for the oxygen. And another way to draw a Lewisdot structure is you can use lines for a pair of electrons, but only if they're bonding, only if they're between 2 atoms. You can't use lines for those outside electrons there. So often a shared electron pair that forms a bond is represented by a simple line. So the Lewisdot could be drawn, the Lewisdot for the oxygen could be drawn the way you see down there at the bottom. And carbon dioxide. Again, we have a similar situation where you have 16 electrons there that you see, but they have to form 3 octets. Well, 3 times 8 is 24. How do you get 16 electrons to form 24? Well, again, by sharing, by creating double bonds. So carbon forms double bonds with each of the oxygen atoms. Notice that all 3 of the atoms have a full octet of 8 electrons. So you started off with 16 electrons, and down at the bottom you have 16 electrons. But because they double bonded and because those shared electrons get double counted for each of those atoms, then you were able to form octets with just 16 electrons. And those are the shared electrons right there. Okay, so this takes care of our lecture on covalent bonding. Go ahead and answer the questions. This is all due on April the 27th, Monday. That'll be a few days from when you do this assignment. And we'll see you tomorrow at the next lecture.